So what are the goals? The goals are to characterize the work output of the motor. The equation is the change in kinetic energy is equal to the total work sum. Our other goal is to create a working engine model that models each individual stroke. And then we analyze this model to the experimental values and find the work discrepancy, which are the other works that are now accounted for in our model. So the methods of testing is we were providing a combustion engine, which was actually modified to run on pneumatic air. And for testing, we use two sensors, a rotary encoder, which is shown in green, and a purple force transducer to measure the force or indirectly measure the torque that the motor outputs. And the lever arm is there, shown in red, that is used to calibrate the torque.
The first thing to do before collecting and analyzing the data was to calibrate the force transducer. We determined the product of the measured torque output and the encoder angle to determine the motor's work. For useful measurement, increase the encoder angle by 10 degrees to reduce noise. And by integrating the torque diagonal displacement curve, the motion of the motor was directly measured. And we analyzed the work energy system to isolate and determine effects of adjusting the system. The red quantities are directly measured and the blue are the unknowns that need to be calculated and found through experimental data. The bore diameter was measured with a caliper for work air term, and it was 52 mm. Each of 5 masses was measured for the calibration curve as shown in the table. The distances between the top-down and bottom-down center in the top-up block were 38.8 mm and 0.89 mm respectively. The length of the moment arm was 127.55 mm.
So, we need to figure out the torque output of our system. This can be accomplished by figuring out how to apply gain to the measurements of the force transducer. To determine this gain, the various weights are placed on the moment arm to determine the torque, multiplying the mass of a collection of weights by the moment arm length, and gravitational acceleration gives us the torque output on the force transducer. We take measurements by adding masses individually until all are above the moment arm, then individually remove those masses. Those torques can then be plotted against the voltage output read then, and a York fit can be plotted to determine the slope and voltage offset. The offset is not necessary to model the system. Observing the plot of the system with no head, the slope of the York fit is 0.22156 nm per volt. The uncertainty ellipses are present, but very small and do not intersect with the fit line. While this may immediately seem like the line is not a good fit, since it fails to intersect the ellipses, the line still consistently lies between points from the torques collected from an identical mass load. The difference in the voltages measured are a result of hysteresis upon removing or adding additional masses, which the ellipses do not account for. Since the fit line consistently remains between these points, the slope should be sufficient. The adiabatic head-on system's fit line has the same likeness to the no-head system. However, the slope is much larger than before, changing from 0.22156 to 0.75057 nm per volt. This makes sense, given that the work of air due to the head would increase the amount of energy in the system, and thus the torque output. After calibrating the force transducer, it's time to collect the torque and angle data. We ran the motor for 3 seconds per speed setting. When collecting the angle data, we noted that the encoder was unable to reference the absolute starting angular position, and so only output a range of angles from 0 to 360 degrees. This would cause the torque data to be overlaid upon each rotation when plotting, which isn't helpful when we want to determine the total area underneath it for our work calculations. We want to determine the work of the motor from when we started to when we stop collecting our data. Thus, we developed an algorithm that increments the angles such that, after every time the encoder finishes a full rotation, the next angular measurement adds to the total positional data. This is more helpful, as it allows us to determine the useful area under a torque angle curve. Upon plotting our torque data to the incremented encoder angle data, We noticed that the resulting plot was rather noisy, making it difficult to determine a good steady-state value. The noise was due to a resolution of the encoder, allowing it to take more points than needed. While more data is usually a good thing, the abundance of points made it more difficult to determine an accurate steady-state torque. To resolve this issue, all torque outputs between 10-degree increments were averaged. This reduced the amount of noise present, and thus made algorithms trying to find a steady-state value more accurate. If we wanted to reduce the noise further, we could have bins with a larger degree increments. Near the steady-state torque, however, there was a higher density of points closer to it than points that would be attributed to noise, which convinced us that despite the noise, it would be accurate enough. We can note that the area underneath the curve is the work of the motor. When considering the work balance energy equation and the no-head system condition, the work of air and any work discrepancies can be ignored. With a steady-state velocity, one can assume no change in energy, so the work of the motor can be ignored. The work terms that remain are the piston, friction, and the motor. The piston work is assumed to be negligible compared to the inertia of the flywheels, leaving only the friction and the motor work terms equivalent to zero. This means that in the steady-state velocity, the work of friction is equal to the negative work of the motor. Looking at the graphs, we can see that the steady-state work of the motor can be approximated to a rectangular area stretching across the bottom of the curve. However, when considering a non-steady-state condition, as was observed when we rapidly turned on the system from a complete stop, the change in energy is no longer zero. Given how we started our system from a stop, there is now a hump in our graphs, the area of which represents the work needed to accelerate the flywheel. To quantify that area, we subtracted the area of the steady-state work from the total motor work. Going back to the work-energy balance, the change of energy must equal the work needed to accelerate the system. Given that the change of energy is no longer zero, the steady-state work is still observed, and the motor and steady-state work terms are not negligible.
Now let's talk about finding the moment of inertia of the flywheel. Obviously, we can just look up the equations for moment of inertia about a circle by just simply looking up online, which will be shown in the references. But also, we know the theoretical mass of the flywheel and the theoretical radius of the flywheel, which is 1.0141 kilograms, and the radius will be 0.07 millimeters, respectively.
Earlier, we found the work of the motor from A to B, the work of friction from A to B, and we determined that the work of the piston is negligible under the assumption of high flywheel mass. So the only unknown left is work of air from A to B. In the four-stroke engine, when the valves are open, which is in figure 1 and figure 4, there is considered negligible work of air since the valves are open. While the valves are closed, as in figure 2, we have compression or adiabatic compression. And in figure 3, which is the power stroke, we have two special conditions. One in which air is injected, which is the adiabatic expansion, and when air is not injected, which
Now to go over week 1 data analysis. Now you can see all the values and numbers that we used on screen, and some important notes is that obviously theoretical and experimental values are not the same, and that's because theoretical assumes a completely rigid system, which means everything is uniform, which obviously in real life it's not. And then also, we can get the individual numbers or workloads for specific parts of the engine. Now, this is a very base case scenario, but overall, we can get those individual workloads for the motor in steady state, for air, or for acceleration, and then we can figure out what's affecting. Now, moving on to week 2 data, obviously, as you can see, the data isn't as refined or organized as week 1, but what we did on this one is now that we can find the total work with those other systems that weren't in place in week 1, such as the piston or the work of air, and then essentially just using the same method, we can find the individual workloads and see what affects them. The thought process behind week 3 is essentially we're doing the same thing but with injected air added, and we have all those formulas and values. We just have to see how that affects work and in turn how it affects our workload.